Hello.
Hi.
Hey guys.
Hello.
Hey. Yeah, Olivia, which question did you have about the homework?
Let me pull up my homework right now. Sorry. It was just about one of the. Okay, it was about the finding the probabilities with sample proportions. I watched the video and it showed me how to do it on a calculator, but I wasn't really sure if that's how you wanted us to do it. So.
Yeah. So what can you walk me through kind of what they said on the calculator? I don't know. Oh,
yeah.
Like,
so
like,
basically. So basically, like the method of finding it on the calculator was, finding the sample population's mean and then the standard deviation, and then plugging that into the thing. I forget what the actual function on the calculator is called. It was distribution and then normal CDF, and then you have to put the lower and upper limits.
Okay. Yeah. So that is that is really the way that you would do these sort of things in real life. But the way I've been writing it down, I just wanted people to, or students to show their work and just kind of go use the table for now. But
The z-score table.
Yeah, just use the z-score table. But the key is like, I mean, that function is really useful because it's just a shortcut for not it just basically does the z-score table stuff for you, and it gives it.
Got it. Do you think you could go over maybe how to do that with the z-score table again? Because I kind of forgot. I was kind of confused on that.
Okay, sure. Yeah, we can definitely do that. Are you okay with the kind of general like z-score table, like how it works?
Yeah, I feel like I understood how to do it until like this last class. Like I kind of got confused with like what we went over last time.
So the idea to keep in mind is that it's exactly the same thing. It's the same z-score table. It's the same, like, you look up like you have a z-score, and then the area to the left of that z-score is the probability under the bell curve. The only difference is that the numbers that we use for the average and the standard deviation have to be adjusted a little bit. So those numbers that you use in that z-score calculation, those numbers are changed for both sample mean and sample proportion. But once you figured out like what the z-score is, the method that you use is exactly the same as for just regular z-scores.
Okay, got it. So after you find what is it called? The P with the little arrow above it?
Yeah, that's called a sample proportion.
Okay, so once you find the mean and the standard deviation for the sample proportion, you just plug those into where the normal z-score formula is?
Exactly, that's right. That's
okay.
That's exactly right.
Okay, got it. Thank you so much.
Mm-hmm. And in general, in statistics, there's a few other tests and like things you can calculate. And like the formulas might be like really look a little bit complicated. The formulas sometimes look a little bit complicated, but the idea is actually the same for a lot of them. Is that you can use some complicated formula to calculate a statistic about a data set, and then that will be your new mean, and then there's another formula for the standard deviation. But once you have the actual number for the mean and the standard deviation, and you know that it comes from a normal distribution, then you just use the same thing that we did before. You can forget everything else and just do.
Okay, thank you so much for the help with that.
Mm-hmm. Yeah, and then we can. I'm happy to go over one, so we can kind of do it. Show you kind of how I want it. You know, how I would like for you guys to explain it. And then, in addition, I'll take a look maybe next week and show you guys like a way to do these on Desmos, similar to how you did it on the calculator. Desmos actually has a really nice interface for these z-score tables. Okay, let me share my screen. Just close the door. Did you guys hear that a lot of Warner Brothers movies are going to be available for free streaming? Well, on HBO. Hey, Quentin.
Hello.
Let me pull up Khan Academy. Okay. So did you guys have any questions on anything so far from the Khan Academy? Any example that you want to kind of see worked out? Any questions about kind of how to do the proportions or sample means? So yeah, any questions at all from the homework that you guys wanted to talk about? And it could be one that you maybe haven't tried yet, if you weren't sure how to approach it. And there was something else here. So And one thing that is mentioned in the textbook is that we want to make sure that, so this is containing sample proportion. So the theory says that in order to apply a normal approximation using the central limit theorem, we really want to make sure that what we're doing here, that in our sample, we want to make sure there are at least 10 yeses and 10 no's in the entire population. Actually, let me think about this. No, not in the sample. And this is translated as we want NP to be greater than 10 and n times 1 minus p. And this is just something you can check given the proportion and given your sample size, you can check if this is true. And the reason that this is important is if your sample isn't large enough and you have a very low number of, so it's actually quite an interesting reason to think about. If you recall, the central limit theorem requires the random variables, the xi, to be independent. So if you pick people, or if you pick rolling the dice over and over, then each dice is going to be independent, and you can apply the central limit. However, can anyone argue why? Let's chat. Yes, yeah, Jim, we can definitely go over one of those examples. The central limit theorem says if you do repeated trials, you want to make sure, and you want to approximate the mean or the average of those trials. You want the trials to be independent. Now, when we do something like this in real life, can anyone kind of say true or false and give an explanation? Is it true that if you pick people at random, then the result of one person is independent of the result of somebody else in your sample?
Wait, are we arguing that claim or supporting it?
Yeah, either way. So there's some. There's like I'm curious what you guys think, and if you have any questions about the question itself, also. So if you roll a die, for example, right? If you roll a die 100 times, there's no argument that each time you roll is completely independent of all the previous rolls. But if you have a random sample, or if you're picking a random sample, are the people that you pick independent, like, and is their distribution of what they're going to say, is it independent of the previous person or all the people before?
Can you choose the same person twice?
You cannot, right? In statistics, you pick a group of people. So how does that? That's a very good question. So what can you conclude from that?
Dependent, because the number of people is finite, right?
That's right. So if there's 1,000, like it's actually a lot like picking marbles out of a jar, right? We talked about this, like if there's 3 red marbles and 7 blue marbles, then the chance of getting 2 red is not. So the chance picking 2 red marbles is not equal to, oh sorry, if you draw twice, if you draw twice, then the chance of two reds, the probability of 2 red is not equal to 3 out of 10 squared. What's the reason that this is not equal to? What is this actually equal to?
Uh, 3 out of 10 times 2 out of 9.
Exactly. So it's not exactly correct.
Mm-hmm. It's close as the population increases, right? Or it gets
exactly. Yeah. If you have 300 red and 700 blue, and you just want to pick 2 of them, so you draw twice. The chance of 2 red, it's not exactly 3/10 any either, but it's exactly kind of like what Kieran said before. It's going to be 300 over 1,000, but now it's not times 2 nines, but it's going to be 299 over 999. Which is really, really super close to 3/10 squared. So does this make sense that why we want the number of successes in our sample and the number of failures, the number of yeses and the number of no's in our sample to be both greater than 10?
Why is it 10? I kind of understand the idea, but that seems relatively arbitrary to me.
Yeah, it is kind of arbitrary. I think 10 is chosen so that it's this idea that let's see here. Yeah, 10 is arbitrary. I think it's just to make the distinction between let's see. How can I say this precisely? Yeah, so if you're so if you have at least 10 of each, then you're always guaranteed to have at least 10. Let's see here. That's a good question. Why is it exactly 10? So this actually explanation that I'm going through doesn't quite, it gives some intuition why we can still make the claim that the draws are independent. It's actually not directly related to NP greater than 10. I think, let me see. NP is greater than 10. So there is another idea here that's important. So the other idea is that if you look at what this is saying, yeah, so another way of thinking about this is if you look at the proportion, so NP, and you're right, it is kind of arbitrary. So for NP to be greater than 10, N times 1 minus P to be greater than 10. Then that tells you that if you rearrange this, that tells you that you want N to be, sorry, not N, you want P to be greater than 10 divided by N. And if you rearrange this one, this becomes N minus NP is greater than 10. Or in other words, N minus 10 NP has to be less than that, or so it's got to be 1 minus 10 over N. So one way to interpret this is that the expected proportion, the overall percentage, if you want to apply this, you want to make sure that you pick a large enough N so that you have this idea that P is somewhere in between 10 over N and 1 minus 10 over N. And the idea, the reason that this is important for applying the limit theorem, and maybe I can show you this visually, is that what we do essentially is wherever P is, we're going to approximate it with a bell curve. It's not actually, like if you do this, this is not necessarily like the sample. If you have like 1,000 people, the number of yeses you can get is actually going to always be, you can't get any more precision than 1,000, right? So technically, the distribution is a histogram. Well, we're using a normal bell curve to express the histogram. And the idea is that if the sample isn't large enough, then that bell curve, or this probability distribution, with this histogram, it actually kind of like looks a little bit weird towards the edge of the what do you call it? The interval. So it might have like, it might be a little bit thicker than you expect here, but then taper off longer. So it'd be kind of like more, a little bit more one-sided. So in that case, the distribution would break down. Rather than, my picture actually isn't very good here. Let me try it again. It would look more, rather than looking like a bell curve, it would look like a bell curve that has a little bit more favoring towards one side. So kind of like that maybe. So there's bell curves that look like that, which isn't really a symmetric bell curve. And so I think 10 is just chosen because it generally avoids, it'll maintain most of the bell curve shape. I'll try to come up with some visualization that would demonstrate why this breaks down. One thing you can imagine is if the probability of success is 0, right, then definitely a bell curve isn't a good approximation. because that would mean that everybody says, everybody is going to be close to the number 0. You wouldn't want to approximate that kind of extreme case with a bell curve, because that's the extreme case where everybody, no matter how you pick, is going to be located at 0. But as soon as you move off a little bit away from 0, you would have a better approximation. It is related to the law of large numbers, but it has to do with the fact that you're trying to approximate a histogram that has to fit between 0 and 1. And if you're trying to approximate it with a normal distribution, the normal distribution has a tail. So, but if it's a distribution between 0 and 1, well, we don't want to use something with a tail if the tail part is going to be like, if the tail shape, the bell curve with the tail might not make sense if the bell curve thing is too close to one of the endpoints. So what increasing n does in terms of the central limit theorem is it actually makes the bell curve really, really, really skinny. So if you're talking about really, really rare events, you just got to make sure that you sample large enough so that even though the number of successes is low, your bell curve will have a really low standard deviation, so it'll be close to the endpoint, and it'll still be a reasonable approximation. So you could potentially have something like if n is equal to 1,000, you will have a really, really skinny bell curve. And let's say p is equal to p could be equal to 0.02. This is going to be 1. You might, the approximation would still be valid because your bell curve will look, really skinny. It might actually even be skinnier than that. Actually, like spikes up. And actually here, it would even kind of go big as it. So I don't know if that idea makes too much sense, but it's just so that the bell curve fits within the interval. Okay, let's go over some homework. Finding the probabilities with sample proportions about camp accrediting. Finding probabilities. And this was regarding, camp accrediting. Good. So let's try this one. But I really like kind of in statistics, like whenever you see some sort of condition, to just, to question why it's true and try to understand. I think it's a really worthwhile thing to do. Okay, so this one is the camp association has 2,400 camps. Okay. They say that they claim that 45% of the camps offer specialized programs. we have P equals 0.45. And the population is 2,400. If we do a simple random sample of 200, so we'll do a sample of 200. What is the probability that between 40 and 50% of those offer the program? And these problems are just a little bit tricky because you have to, because we're talking about the distribution of a proportion or percentage. So you don't want to confuse the percentage, which is kind of like the, which is like our X value, and it also happens to be like a probability. You don't want to confuse that with the probability of an actual like event of the sampling distribution. So these numbers, 45%, 40, and 50, they are like X values. They're like, you know, they happen to be percentages, but really I think of them as like when we're talking about elephants, like the height of an elephant or something like that. But we're going to talk about what's the chance that a sample has a probability, has a measurement that falls in this range. Okay. So let's do this. So we have P equals 0.45. The sample size is N is equal to 200. And the 2,400 actually isn't, let me think here. Yeah, there is one thing. I believe you do want to make sure that your sample, I think, is less than 10% of the population, which in this case it is, and that is for the. I think that has to do with the independence. But yeah, the 2,400 isn't super relevant. And now we can just plug it in. Oh, yes. So we find that mu of p hat is just the regular p. It's 0.45. But then sigma of the sample proportion, p hat is a sample proportion, is going to be square root of p times 1 minus p divided by n. Yeah. But so if the sample is, if you're picking too large of a sample, if you're picking too large of a sample to test the sample proportion, you know, if you pick if you pick everybody, right, then just to kind of do a thought exercise, if you do if you pick all, if your sample is 2,400 people, then your there's no more randomness. Like you're always going to get 45%. So yeah, I think this theory breaks down a little bit if you have too large of a sample. What do you do if your sample is very large? I mean, it's more accurate though if it's large, which is good. You actually probably, I think the thing with the theory is that the theory, this central limit theorem exercise, would give you a, it will kind of be a lower estimate on the probability. But in fact, you'd have, if you take a larger sample size, you get more accuracy, and especially if the sample size is close to the population size, then it's like you get almost perfect accuracy. So you could still use this approach, but I think it would be it would be like the lower bound on the accuracy.
So I understand why once you get like larger, wait, let me take a moment to figure out how to say this. I understand why you want to do this with a sample less than 10%, right? Because as you get closer and closer to the real sample, it gets less and less random.
Mhm.
But what if you had like 1,200, which is half of the sample? There is still variance there, but you can't use this formula for it. So I guess I'm
Right.
just kind of curious what you would do.
Right. So you could still apply this formula, but your results would be even better. Like, let's say you'd find, okay, I think that there's a, like for this question, let's say we get like 30%. What we would find is actually the chance would be even higher than 30%. So we would give like a lower bound on the probability. I believe that's what would happen. But the reason we say it's not like, it's not a very good approximation to that answer, but at least it gives you some lower bound.
Wait, so this formula works if it's under or over 10% of the total, right?
Yeah, let me look that up exactly.
Yeah.
When can you use normal approximation?
Like p times n has to be greater than 10, and p times 1 minus n has to be, or the other way around. That has to be 10. It has to be like normal, right?
Yeah, so n times p and n times q have to be greater than 10. That's a little bit different than the population. Sample is less than 10% of the population. Yeah, this is the 10% condition. And some people say it's better to even have a 5% condition. Now, like this 10% condition, if for practical purposes, is not very important because most of the time you want to ask a question. Like most of the cases where you do statistics, you want to ask a question that's that you're trying to understand, like for a few thousand, a population of at least a few thousand, maybe a few million, or even 100 million, and your sample is only going to be like 100 maximum, or maybe 1,000 or something. So in practical purposes, this condition is almost always met because, if you can measure 50% of the population, well, just do that twice and you get 100% of the population. So that's kind of the philosophy there. But yeah, the theory, the mathematics of it breaks down because if your sample is more than 10%, then it's the 10% condition is actually this thing that we were talking about in the beginning of the class. The 10% condition will mess all this up. So it won't be this won't be an accurate way to do it, but it will give you at least the lower bound. Like whatever you do, if your sample is more than 10%, will be more high probability of being within a region near the sample proportion if you do this. The NP and N minus and Q thing, that has to do with getting messed up around 0 and 1. like trying to fit a bell curve close to 0 and close to 1. It has to be a skinny enough bell curve to fit next to 0. It has to be skinny enough to fit next to 1 in order for the approximation. But yeah, it is in this case to make sure that our approximations are valid and the number that we talked about is valid. You would check that. You would say, okay, this is less than 10% of the overall population. Okay, let's calculate this. So this would be 0.45 times 0.55 all over 200 and square rooted. Did anyone calculate this number? Point 0.035, I like it. This is 0.035. So what it tells us is 3 percentage points is 1 standard deviation. So most of the time, if we take a sample of 200, we should expect that that would be distributed about between, most of the time we'll get numbers that have a probability, that have a outcome between 0.42 and 0.48 roughly. So now we want to know, so we have our sigma, it's 0.35, our mu is 0.45. Let's find the probability that p hat is between 0.4 and 0.5. Well, let's find the corresponding x values. So, sorry, the corresponding z-scores corresponding to these x values. So that would be the z-score, the first z-score would be 0.4 minus 0.45 all over, so I'm just doing x minus mu over sigma, 0.035. This is negative 0.05 all over 0.035. And this simplifies as 50 over 35, which is 10 over 7. I don't know what fraction it is, but it's negative. You can just plug it into the calculator also. This is negative 10. Oops. Negative 10, 7 is negative 1.42. And the second z value is the one with related to the upper bound, the 0.5 minus 0.45 over 0.035. And this is 1.42. It's just the opposite side. Okay, now we have a nice probability in terms of z-scores. What's the probability that the z distribution is between 1.42 and negative 1.42? And then you can do this by taking the probability of z being less than 1.42 and subtracting the probability that z is less than negative 1.42. Any questions at all up to this point? Is it, and please say yes, is it clear, like once you get to this step, like once you find this and once you find this number, the rest of it is just the regular normal distribution stuff. And that's how it works for a lot of these. There's different situations where there's other formulas for sigma and other formulas for mu. Mu is always pretty easy, it always makes sense, but sigma sometimes has some weird formulas for other situations. But once you get mu and sigma, you can do all just this. Okay, and then looking at the z-square table, Anyone want to tell me what they got here? Okay, overall 84%. Anyone else confirm that?
Yeah, that's what I got too. 84.5%.
Okay, awesome. So just be careful here. Really, you have to stay like sharp, stay on your toes. Like there's percentages that we're talking about. There's percentages that refer to like the sample proportion, and then there's percentages that are talking about the probability of the sample proportion being in a certain range. So make sure you're very clear on those distinctions, because it can be a little confusing, because there's percentages that are kind of measurements, there's percentages that are probabilities. So yes, 0.035 is only in relation to the sample. Regardless of how large the population is, the sampling distribution only cares about the probability and the size of your sample. The sampling distribution, or the sigma, doesn't care about the sigma p hat. It doesn't care about how big your population is. It only cares about what sample you got. The population is just important so that you can check the 10%. Okay, very good. Any questions? Any other questions on this example?
I just had a really quick one.
Yeah.
I think I know the answer, but I just want to make sure. This sort of like idea only applies to like situations with like yes or no answers, right?
Oh, yes. So this is a specific case. If you think about it, this is really just a specific case of yes or no answers, like 0, 1 responses, or basically just 0, 1 responses, like yes or no answers. But this is really a specific case of the sample mean, right? Because if you record a 0 for the no and the 1 for the yes, then the mean of all those responses is p hat.
So the formula where it's p times 1 minus p over n square root, that's only if there are two options?
Yes, that's where you consider that's where you're counting successes, or you're counting the proportion of successes, which means it's a random variable that says you get 1 point if the person says yes or succeeds, and 0 if there's a failure or they say no.
But in like something like some height or dice rolls, like anything that's like a range of values, we need to find the sigma. Like we're just given sigma and then we find sigma p hat.
Correct. So we'll talk about it in a second. But well, maybe we'll talk about it next week, maybe later today. Yeah. That is a very good question. This is for heights, right? That sigma that I'm giving you, I just kind of come up with it in thin air. It's actually something that's, you would technically need to measure everybody and calculate the standard deviation to understand the standard deviation of the population. But if you think about it, there's like a little bit of a circular logic happening there. Like, how can you measure sigma if you don't even, like, if you can measure sigma, then you already know the entire population. So why are you doing any of this? So we'll see later that you actually don't know sigma. This was just, I give you these examples with sigma just to kind of get the ball rolling and show you some of the ideas. In practice, you don't have sigma, you have S, which is the sample standard deviation. And it's kind of similar for proportions. For proportions, it's nice because if you know that, if your random variable is just yes or no, and you know the probability of your people saying yes or no for your entire population, then using that table, we can calculate exactly what sigma is. Sigma is going to be exactly this value, square root of p times 1 minus p. So, you know, if you think about the logic of what these problems are saying and how practical they are, why, you know, I guess I could be interested in this type of question, but most of the time we're working backwards. We rarely, if I knew that 45% of camps offered specialized programs, then I'm probably not going to need to do statistics on it because I already know the answer. This is you know what I mean? Like if you usually in statistics you want to understand something about the population, but if you already have exactly what p is, then you don't need to do the stuff that p has. Well, we're just doing this for now as a examples to kind of get our hands dirty a little bit with the formulas and some of the ideas. But that brings us to the next idea, which is like, okay, well, this is all good, this is all good and well, but like what we've done so far has been kind of abstract and not very practical because, you know, like I said, where do we get the sigma from? And if we already know p, then, you know, why are we even doing this? So what we actually want to do is we go in reverse. So that means that you don't know anything about the population, maybe just how big it is. Maybe you don't even know that. You know there's some population. All you have is your sample and your p hat. That's all that you, and your observation. You just did it one time. And the theory is, well, can we go backwards and maybe conclude something about lowercase p? Well, that's really what statisticians try to do. But yes, the official nomenclature is a hat, p hat. Well, sometimes they say maybe carrot, but I think I usually hear it p hat. So to do that, so in practice, we don't know anything about the population. About the population. We don't know sigma. We don't know p. You know, there's a lot of things that are missing. We only have your data. We only have the data. We only have data for this thing. And so what we're going to do is we're going to try to estimate. So our goal, what we can do with this data, and the things that we can deduce from it is we're going to work backwards. Work backwards from our sample to create a confidence interval to create an interval that has a high chance and also I'm going to put mu in here. So keep in mind these are, I'm going to write it in, these are parameters that in practice you don't have this. We're just trying to estimate it. There is a high probability usually set to 95% of containing the true parameter. So basically the main idea is we take our data, we observe something, and we say, okay, well, based on this observation, I'm going to do a calculation, and I can tell you that I think that the true result, the true proportion, or the true mean has a 95% chance of being in this given interval that I'm going to construct. So how do we do that? So let's assume, for now, we're going to assume something. This is about the margin of error and confidence intervals. So for today, we're going to assume that we somehow have this, we have access to sigma. And next week, we'll talk about how to deal with that. But so first, assume that we know that elephant weights have a sigma of 200 pounds, and we sample, let's say, 16 elephants, and find and discover that X bar, the sample mean, X bar is equal to, let's say, 2100 pounds. This is X bar, right? We don't know what mu is. The question that you might be given is, find an interval that has a 95% chance of containing mu. So what that means is that, I'll explain what that means in a second, because it's a little bit confusing. So find a 95% confidence interval okay. So the thinking here is that our answer is going to be something like maybe 2,000 to 2,200. So we're going to find the exact number, the exact interval. And the idea is that this interval that we created has we're going to say it has a 95% chance of having the true value. And the reason we can say that precisely is because the thinking is that if we were to do this experiment where we just pick 16 random elephants 100 times, so do it 100, pick 16 random elephants, repeat that experiment, do that sampling 100 different times. If we look at the intervals that you create each of those 100 times, 95 of those intervals should have mu, and about 5 of those intervals will not have mu. That's why we say there's a 95% chance that an interval constructed in this way would contain mu. So how do we go about this? We say, okay, if I want it to be with 95% confidence interval, first let me figure out what my sigma X bar is. That's going to be 200 all over square root of 16, which is 50. And the kind of reverse reasoning is that I'm going to see how far away can I be from 2100 so that I know that my, that there's a good chance that I'll observe 2100, given that my mu is something a little bit further from 2100. So there's, here's 2100, which is our sample. We want to pick a z-score that, so there's a comment I can make, but I'm just going to draw this picture. We want to pick a z-score that captures, there's a 95% chance that our numbers are within here. So if you look at 95%, if you want a body of 95%, that means that you want this. Yes.
95% fit in there? Yeah, what does that mean? I'm sorry.
Yeah, sorry. So so you can make like try to make an interval around 2100 that you could say like if you try to draw a bell curve around 2100, pick an interval that has 95% of the data, or would have 95% of the probability.
Okay, so like there's 5% on the outside and 95 on the inside.
Exactly, that's right. And the thinking of this is a little bit backwards because what we've done so far has been the opposite, where we're given mu and we want to say what's the chance of an observation happening. But now I'm given an observation and I want to say what's the chance of mu being close to that observation. There's an interesting reversal that we're applying here with the bell curve. But the simple way of thinking of it is just create a bell curve and use that sigma, which is going to be 200 over 4. So using that sigma and using 2100 as the middle of the bell curve, figure out what the threshold is so that you capture 95% of the data in your interval. That tells us that this has to be 2.5%. And the other interval also has to be 2.5%. And you'll see that there's just going to be one number like that we use all the time. So if you look at the z-score table, z table, and you look up inside the table for 0.975, you get 1.96. So that tells us that this corresponds to a z-value of 1.96, and this one corresponds to a z-value of negative 1.96. And this number is just really important for 95%. We just use it, we just know this number. 1.96 standard deviations away, and to the left and right will capture 95% of the data. So we can now construct our interval. So the formula for the confidence interval is as follows. The confidence interval is equal to, I'm just going to write it here, 95% is equal to x bar minus 1.96 and sigma over root n, comma, x bar plus 1.96 and sigma over root. So this range of values is our confidence interval. Oh, that's right. It's basically, it's a little bit less than 4 standard, like overall four standard deviations, like why. But yeah, that's correct.
Would
Very
1.9
close.
change if the complement
What
is
was
a different number, or will it always be 95%?
yeah? It's almost in practice. You always like 95% is a pretty good probability. Sometimes you want to have a really like high confidence interval, like 99%. Then you would have to make you would look in the table and your z-score to capture 99%, you make it a little bit wider. Because the wider you make your confidence interval, the more likely it is to have the true value.
Will we have to practice with like low confidence intervals, or do we just never want it low? Like 50% or something like that?
Oh, no. You never do 50. Like, you wouldn't do 50. Like in practice, you wouldn't say, oh, there's a 50. You wouldn't report to someone, hey, I'm going to give you an estimate that where I think the answer is, and there's a 50% chance I'm right.
Yeah.
You usually want it to be at least 90. You do at least 90, and it depends on like what your threshold for mistakes are.
All right. Thank you.
And if you see, this kind of brings up the idea of test design, right? Let's say you want to have a 95% certainty, and you have some threshold for making a mistake. Well, if you want to make your answer more accurate, do you guys see that you can change your n? If you increase your n, you're going to make these numbers smaller. So you'll make your margin, your interval smaller. These numbers, 1.96 times sigma over root n, this is called the margin of error. So let's do an example, then we'll see how you can use this margin of error formula to come up with the desired sample size if you want to be within a certain, like, you want to make sure that you are within a certain tolerance. So yeah, just plug in here, you get your confidence interval is going to be 2100, where is it? Yeah, 2100 minus 1.96 times 50. And then
Sigma bar, not. Oh, that is sigma bar. Never mind.
yes, exactly. That is this. That's right. 2100 plus 1.96 times 50. And 1.96 times 50 is 98. Yeah, so this is going to be, the interval is going to be 2002 to 2000 or 2100. That tells you that, you know, there's a 95% chance that this interval, based on your methodology, there's a 95% chance that the true mean is in this interval. There is a chance, though, that you know, maybe you just picked elephants and you picked them randomly, and somehow you got elephants that were all really overweight, and that interval that you calculated, maybe it doesn't have the true mean. That could happen. But most likely your interval has the true mean. You don't know where it is. It could be 2003, it could be 2197. You have no idea where it is, but you know that the chance of it being in there is 95%. And so there's kind of a little bit of like a philosophical thing that's happening here. It's even still when I think about like how you make a confidence interval, what's really happening in my mind is that you don't know where the mean is. So there's some mystery mean. You don't know where it is, but you want to make sure that it's within. There's a like the thing that you observe. There's a chance of it happening. The sample mean. So the sample mean, you know, you want to make sure that this is within the 95% body within the sample mean. So you can kind of say, well, therefore I want my confidence interval to be things that are 1.96 standard deviations plus or minus from 2100. So if that
this
idea
might-
makes sense.
What if we use 0 and 1? Can we get it 100%, or will it just not work?
Well, can you say it again?
Like-
What is
Like instead of the interval being 95%, what if the interval was 100%?
oh, very good question. What do you think? That's an interesting abstract question.
I mean, I feel like that's too convenient, so it probably won't work.
Well, what do you think would be the answer? That's an interesting philosophical question that actually has a good answer. So if you want 100%, right? What's
Yeah.
the z-score for 100%?
I don't know. It only
What
goes
was
up
it?
to 98.
But the normal curve, because it's e to the negative x squared, right? It's always going to have a little bit of a chance of like a black swan event or something like that, right? There could be potentially, even though there's like for normal distributions, like 1 in a million chance, you might be able to observe something that's like 10 standard deviations away. Maybe
Yeah.
1 in 10 million, 1 in a billion chance of observing something that's, so the number of standard deviations is infinite to get 100%.
Okay.
So therefore, to guarantee 100% that you guess the right answer, or that your interval has the right answer, your margin of error has to be infinite. So you say, oh yeah, I think I think the average elephant weight is somewhere on the real number line. Then yes, that's a true statement with 100% accuracy. But yeah, that's the cool thing about the bell curve is that after 3, the likelihood of observing something that's more than 3 standard deviations is what 2 10,000ths. So it's really, really rare. So you can get a pretty good accuracy with a fairly low number of standard deviations. And generally, all the time, people just use 95% because when we go to the next topic, I'll share with you that it was some statistician that kind of started doing that, and there was another statistician who was upset about it. But that's what we do nowadays. Okay, let's see here. So this is how you can construct a confidence interval. Sometimes you'll be asked to do a 90% confidence interval. They might ask that in the homework. If it's 90%, you have to remember that there's going to be 5% on each side. So you got to look up 90.95 in the z table to get the corresponding value. And then you do the same exact. The interpretation, if you ever encounter this on like SAT or other classes, they always want to make sure that you understand the interpretation of its confidence interval. So what this means is that it doesn't mean that like 95% of the data is in here or anything like this. This interval doesn't say anything about the distribution of your data set. All it says is that, so interpretation, that 95% of intervals constructed this way contain the true mean. And this is a really kind of powerful statement because it's cool that we don't even know what mu is, but we can say something about how likely an interval is to contain it based on some observation. Another way of saying it is the interval has a 95% chance of being correct, or of containing mean. That's all this says. This does not say, I'll tell you what it does not say, what a lot of people often get confused with. This does not say, what it does not say is that 95% of elephants have weights between 2002 and 2198. I always like to, have you guys seen this question on the SAT? I've seen this quite a bit. They like to ask about like, what is the interpretation, and they always have something like this, which is a little bit confusing if you haven't really thought about it carefully. We don't know anything about the distribution of elephants or anything like that. We just know, we just observed one sample and that's it. Then we have a sample mean, and from that we're going to extrapolate and say, I think there's a good chance that the true value is in this neighborhood. Yes. Clear? Any questions? Is it clear why the does not say thing is incorrect? Okay, last thing here is how to decide on n. Oh, and by the way, you can do the same exact thing for proportion. You can find a confidence interval like when polling, right? When they do polling, they give a margin of error. If you follow any of the things with the polls recently, they always say, okay, well, there's a chance that Biden was ahead by like leading like 55 to 45, and there's a margin of error of like 3%. So those kind of analyses come from exactly the same approach, but instead of X bar, you would use P hat, and instead of sigma over root n, you would use, you actually can use 1/4, sorry, 1/2 over root n. I'll just mention that really quickly here. So let's just move this over. So very similar approach for confidence interval for the true proportion. Using the sample. So we find that the confidence interval is equal to the 95% confidence interval would be equal to p hat plus or minus square root of, and this is where I'm going to kind of do something a little bit different. So you might say, okay, I'm going to use p hat over root n times 1.96, and then p hat plus or minus root n 1 minus p over root n. But many times, this isn't maybe the best thing to use, because we don't actually know if the standard deviation is not actually this. The standard deviation is actually p times 1 minus p. So what we do is we say, well, wait a second. Look at p times 1 minus p. What is the biggest that this can be? Does anyone know what the biggest value for p times 1 minus p is? When is that number going to be the biggest possible, and what would it be?
5.
What is it?
Or no, 0.25.
Yeah, exactly. This is actually the graph of a parabola. If you write like sigma squared equals that, and you plot these expressions, you see that this is a parabola with roots at 0 and 1, and therefore the highest value is right in the middle. The max value, and this is the p-axis, and this is the y-axis or whatever. The maximum value happens right there. So at p is equal to 1/2, the variance is equal to 1/2 times 1/2. Therefore, the max sigma is equal to 1/2. So many times what we do is we actually replace this. We don't use this. We just use 1/2. Because if you're making the sigma as big as possible, then if you want to make a 95% confidence interval, if you just put a 1/2 in there, instead of the square root of p hat 1 minus p hat, whatever the true value would have been, you're actually giving yourself a little bit of a bigger margin error than you need to. So that's okay to do because you care about making sure that your interval contains the truth. So if you stretch out a little bit bigger, then you actually even have a higher chance than a 95% chance of containing the true value. So usually for proportions, we just use 1.96 or whatever the appropriate z value is times 1/2 times 1 over root. That would guarantee that it's at least 95%. Okay, any questions on that idea?
I think I totally understand the math, but I forget what P is a symbol for.
Well, P is the number, the sample proportion. Or,
Okay.
sorry, P hat is a sample proportion. P is the population proportion. And keep in mind,
Population proportion meaning,
like mu.
okay,
There's a very one-to-one analogy here. P is like mu, and P hat is like X bar.
yeah, I understand that, but so is P the population, the total population?
P is the proportion of the total population that would say yes.
Okay, got it.
And it's exactly like, this is why we do polling, right? When people do polling, they want to know what P is. Like if you knew right away what the outcome of the election would be, or like if everybody voted and everybody who voted, you knew what they would say, that would be is if you knew P. But when people poll, the election hasn't happened yet. We don't know who's going to vote. We don't know what they're going to say. So they call people up and they ask them, hey, how are you going to vote? That's how you find P hat. And then you use that to estimate the P, which is the outcome of the election. And as we see with this recent election, there's a lot of ways for these statistical methods to go wrong, and it really comes down to sampling. Sampling is a very delicate thing that can be difficult to do. Sometimes it's easy, but sometimes it could be a lot of problems. Okay, so how to decide on the appropriate n? And it's just simple algebra. So let's say we want to know the true mu for elephant weights. Weight. to within 10 pounds. So we want a 95% confidence interval. Or we want to have a good estimate, maybe. We want a good estimate for the true elephant weight to be within 10 pounds. So 95 confidence interval. This is the same as asking for a 95 confidence interval with margin of error equal to 10. So then you just set up this equation using everything that you're doing. So if it's 95% confidence interval, you know that the margin of error is 1.96 times sigma over root n. This is going to be 1.96 times 200 all over root n has to equal to 10. Or actually it has to be not equal to 10, but we want it to be less than 10. We want a margin of error that's less than 10. And then you can solve this by cross multiplying. You get 1.96 times 200 all over 10 has to be less than root n. Square both sides. So n has to be greater than 1.96 times 200 all over 10. And what is this? 400, this is roughly, n would have to be greater than 20 is 400 times 4, about 1600 roughly. So you'd need quite a lot of elephants to get pretty accurate estimate on what the true average weight is. But if you had 1600 elephants, you could say pretty confidently that their that their average weight, whatever that sample you observe, the average weight would be, the true average weight would be within plus or minus 10 of that sample. And this example also illustrates, I think, a comment that Kieran made a while ago, that like as you increase your sample size, you get less and less benefit. Like you need to increase your sample size quadratically in order to keep cutting it by the same factor. Any questions on how to find the optimal sample size for a desired level of confidence? Sorry, desired level of accuracy? All right, hopefully these examples will help you. I'll take a look on the homework. I think they should help you with the rest of the homework. Okay, I'll do the next. I'll post the next assignment so that you guys have it, but I'll make it due on Friday, or maybe next Sunday, so that we have some time. But you can get started. All right, guys. Any questions? Anything at all that is a little bit unclear, or?
Yeah, so I just wanted to make like certain of this because I feel like this was the understanding in my head. So when you're using mu and stuff, that's when you have like a number that it's the average of. P is more like a probability of a yes or no question.
Oh, yeah, okay. So be careful. Yeah, P is, you're right. P is a probability of yes or no question, but it's also equivalent to the proportion of the population that would say yes or no.
Yeah. Okay, that makes sense. It's just, I was kind of having trouble keeping track of the meanings of all the different characters, but yeah, all that clicks now.
Mm-hmm. All right, guys. Yeah, I'll stick around if you have any other questions, but I hope you have a great weekend. Message me if you're stuck on anything as you're working on these. When I first learned it, I was very confused. So it's definitely okay to be confused on some things, and hopefully, just keep asking me questions if there's something that within a notation or concept that you don't believe or you're having trouble wrapping your head around.
Thank you, Daniel.
Definitely. See you, Karen.
Thank you, Daniel.
Thank you.
Bye.